So, ladies and gentlemen, you are welcome. So, in today's video, we are going to look at the concept of inorganic chemistry, specifically transition element. So, ladies and gentlemen, when you say transition element, they are metal and they are best defined as an element that have partially been d orbital. So if you ask to define transition element, the best way to define transition elements are those elements in periodic table that have partially been d orbital, and that is what you call transition element. So whenever you see an element that have partially been d orbital, so that element is described as a transition element. Like for example, because as I said, we define them based on their partially filled d orbital. Whenever you have an element with partially filled d orbital, so that element is described as a transition element. So let's give examples. Of course, scandium is one of the transition elements and it has an atomic number of 21. Although we have different series of transition element, we have first transition series, we have second transition series, and we also have third transition series as well as also fourth transition series. But I think let me just try to give the definition from here. So scandium is an element that has atomic number 21. So how do you arrange the atomic number, or how do you actually arrange the electrons of scandium? So you need to follow our above principles. And what is above principles? And above principles is a rule that said that electrons are arranged from lower energy level to higher energy level. That is where we have this pictorial representation: 1s, 2s, we have 2p, then we have 3s here, 3p, then we have 3d, we have 4s, we have 4p, we have 4d, we have 4l. So even from here we can stop, and of course we can draw the electronic configuration of the element using. So you see the arrangement start like this. We start with 1s, then 2s, 2p, 3s, and then 4s, then we have 4p, 3d, 4s. So what does that mean? It means that you are arranging electron first from 1s, 2s, 2p, 3s, 3p, 4s, then 3d, 4p, 4d, 4l. So this is scandium with atomic number 21. So what we are going to do now, to arrange the electron, we know that each of these orbitals accommodate a maximum of number of electrons. So like for example, S accommodate a maximum of 2 electrons, P accommodate a maximum of 6 electrons, and D accommodate a maximum of 10 electrons, while F accommodate a maximum of 14 electrons. So now what are we going to do? So we have this. So we are going to use this above principle and then follow it up with this. So therefore now we are starting with 1s. So 1s, that's accommodate a maximum of 2 electrons. So we add 2 electrons. Followed by 2s, so we have 2s2, then we have 2p. P accommodates 6, so we have 2p6. And then the next one is 3s2. And then after 3s2, then the next one is 3p6. Then the next one is 4s2. And then after 4s2, then 3d1. So it's 3d1. So now we are to count. So we have 2 plus 2 making 4. 4 plus 6, 10. Well, we have 18, we have 20, then we have a total of 21. So this is how to draw the electronic configuration of scandium. So scandium has a total of 21 electrons from this electronic configuration. But if you look at the 4s and 3d, Based on the energy level, we'll realize that the energy levels of 4s is greater than that of the 3d. But because of the closeness in terms of their energy level and the smaller atomic size of 4s and 3d, so that is why we change their position. So because based on the number, the 3 must come first before 4s. So that is why we are now taking d with this side. So instead of writing the configuration of scandium like this, so the best way, even sometimes we do summarize this. Because when you have 1s2, 2s2, 3, 2p6, 3s2, 3p6, this give you, this is the something as the electron configuration of argon. So sometimes, if you want to draw the electron configuration of transition element, instead of writing all this, you just summarize it as argon core. Argon core, meaning that after writing the electron configuration of argon, then it will now follow as argon configuration. Then we have 4s2, then we have 3d1. But because of the 3d must come first before 4s, that is why we rearrange them. We now have argon configuration, then we have 3d1, then 4s2. So now, according to the definition of the transition element, is this scandium transition element? The answer is yes. Why is it that it is yes? Is because if you consider this 3d is partially filled, because it only has one electron. So now, if we have, let's say, 3d10 here, in the case of zinc, zinc is also one of the elements that is, of course, within the first series of transition element, and the atomic number of zinc is 30. So when you are to draw the electron configuration of zinc, it is going to be argon core, then 3d10, then 4s2. So if you can now see clearly, 3d has 10 electrons here. So it is not partially filled, rather it is completely filled element. So as a result of that, zinc is not considered as a transition element. Rather, it is a d block element, because it is, if you check the third transition series, you'll see that the zinc is there. So zinc is a d block element because you can find it in the first series, and it is also in the similar series with scandium, titanium, vanadium, chromium, cobalt. They are all in the same series, but according to the definition, because transition elements are those that have partially filled d orbital, so that is why zinc is not considered as a transition element. Rather, it is considered as d block element. So let me just give another example. Because apart from scandium, you also have manganese, and the atomic number of manganese is 25. It is 25. So therefore, it's now going to be argon configuration. Then we have 3d4s. So in the case of manganese, of course, although I think I have to write the electron configuration of all these elements, the first 10 transition element. So I think that would be better. So let me start with the first element is scandium. So I already wrote it here as number 1. Then we have number 2. Apart from scandium is scandium. The next one is, of course, vanadium. So titanium is the second element. So Ti is titanium, and the atomic number is 22. So it is now going to be argon configuration. Then we have 3d4s. So we have 4s2 here, then we have 3d2. So the third one is vanadium with atomic number 23. Then we are now going to have argon configuration. Then we have 3d4s. So we have 3d4s. So we have 4s2 and 3d. We have 3d4s. So here it is going to be 10. So after vanadium, the next element is chromium. The next element is chromium Cr, so which is number 4. Number 4 is chromium, and the atomic number is 24. So therefore, we now have argon configuration, then we have 3d4s. But here, ladies and gentlemen, there is something very important. So it's 24. So instead to write 2 here and 4 here, what usually happens, because as I said, S accommodate a maximum of 2 electrons, P accommodate a maximum of 6 electrons, while D accommodate a maximum of 10 electrons. So instead of putting 4 here and 2 here, is better to add 5 here, so that you have half of the 3D here and half of the S here. So this is what we call half-field stability. So it is more stable to have 5 here and to have 1 here, because generally elements, they are trying to reach, or the element in periodic table, what they are usually do, they're trying to attain stability. So for the element to attain stability, it is very, very important to look at a way that this element will be more stable. So instead of putting 4 and 2 here, it will be less stable compared to putting 5 and 1 here. So that is why we now add 1 here, so that we add 5 here. At the end, we will have what we call half-field stability. So because of half-field stability, when element reach half-field stability, it is more stable compared to those elements that are not stable. Sorry, it is better than the elements that are not in that half-field configuration. So because of half-field stability, that is why you add 5 here and you add 1 here. So as I said, elements generally are trying to reach stability. So to reach that stability, the element will follow a lot of different mechanisms for them to be that stable. So because of this half-field stability, that's why we have 5 here and then you have 1 here. So after chromium, then the next element, so we have 1 there, we have 2 here, we have 3, we have 4, and then this is number 5, that's in the case of chromium. Sorry, manganese. So the manganese have 25, so here we are adding 2, and then here we are adding 5. So I can even ask you, between manganese and chromium, which one do you think is more stable? The answer is chromium. Because of this high-field stability, it makes chromium to be more stable than the manganese. So that is for the manganese, and then the next one after manganese is number 6, which is iron. Iron is Fe, atomic number 26. So it's going to be argon configuration. Then we have 3D, 4S. So we have 3D and 4S. We have 4S2 and 3D 6. So we have 18 plus 2 making 20 plus 6 making 26. So that is for iron. And then the next element after iron, so the next element after iron is, of course, cobalt. It's cobalt, which is number 7. This is number 7, so it's cobalt, Co, with atomic number 27. So then we now have argon configuration, then we have 3D 4S, so we have 4S2, and then we have 3D7. And very importantly is number 8, that is apart from cobalt, is nickel. So the atomic number of nickel is 28. So it's now going to be argon configuration. In bracket, we have 3D 4S2, and here we have 8. Then the next one is, of course, copper with atomic number 29. So it's now going to be argon configuration 3D4S. So in this case, the issue of stability also comes into play. So instead of adding 9 here and 2 here, we add 1 here and then we add 10 here. So instead of adding 2 here, we add 1, then the remaining electrons are completely added here. So, ladies and gentlemen, I want to say something here which is very, very important. So you should know that always elements are trying to reach stability. So it is more stable to add 3d10 here than to add 9 and 2 here. So that is why D here is completely stable and this one is half stable. So as a result of that, the chromium is more stable than the nickel and some other element. So then the last one is zinc, which already written here as number 10. So 3d10 and 4s2. So now according to definition, the transition elements are elements with partially filled d orbital, are element with partially filled d orbital. So can you consider this as a transition element? No, because the 3d is completely filled. Can you consider copper 29 as transition element? The answer is no. This copper, especially like for example, one thing that we are going to discuss is the properties of transition elements. So as we are going to discuss on the properties of transition element, you can see how some of the properties are applicable to some and it may not also be applicable to some. Like for example, let's say scandium 21 plus. So is scandium 21 plus transition metal? No. Because this plus means that it loses one electron and that electron loses by scandium. 1 plus, it means that it loses one electrons from the 3D. So because at this point it is in the case of scandium 3 plus, so no electron in 3D. So because there is no electron in 3D in the case of scandium 1 plus, so you cannot consider scandium 1 plus as a transition element. So also in the case of copper 1 plus. So in the case of copper 1 plus, it means that only one electron is loose or it lost from 4s, and that is why copper 1 plus can be considered as the transition element. In addition, zinc 2 plus. If you have zinc 2 plus, it means that only 2 electrons are lost from 4s and then the remaining 10 electrons in the 3D remain there. So you cannot consider it as a transition element. So ladies and gentlemen, by definition, when you say transition elements, they are elements that have partially filled d orbitals, and this is how to write the electronic configuration of these transition elements. So very importantly, ladies and gentlemen, because there is something very important that I have to say here, especially the quantum numbers. So we can decide to say, okay, what are the quantum numbers of some of these transition elements and how you can use quantum numbers to generate electronic configuration of some of these, to generate or to identify a particular transition element. So it's very simple, ladies and gentlemen. Let's say now you are asked to determine the position of, let's say, 25th electron, 25th electron in cobalt, 25th electron in cobalt. So how do you actually determine all 4 quantum numbers of the 25th electrons in cobalt? So it's simple. Let me just click here so that you can determine the quantum numbers of the 25th electron in cobalt. So one thing very important here, we also need to have a good understanding of Hund's rules of maximum multiplicity. So it's 27. So we have carbon configuration, and then we have 3d7, and then we have 4s2. So where do you expect to have 25th electron? So you see we have 18 here, and you know that when writing equation, you must fill the 4s electron before going to 3d. So it means that this 4s2 is where you have your 20th electron. And then for your 21st electron, you can come down from this 3d7 is here in the 3d7, and in this 3d7, of course, according to our principle, there are 5 subshell for 3d orbital. So therefore, we are talking about fifth electron. So we have to arrange them according to our principle. He said that electrons are arranged singly in degenerate orbitals before pairing. So we are now going to arrange them singly. So let me start with this. So the 25th electron. So this is the 20th electron. So this is the 21st. This is the 22nd. This is the 23rd. This is the 24th. This is the 25th. And this is the 26th. This is the 27th. So these are the 7 electrons from this 3D sum. So we are talking about the 25th electron, and where we have 25th electron is here. So now we want to determine all 4 quantum numbers of cobalt here. So how do we do it, ladies and gentlemen? It's simple. Of course, we have 4 different quantum numbers. We have principal quantum numbers represented as n. We have principal quantum numbers represented as n. And then we have azimuthal quantum numbers represented as L. And then we also have magnetic quantum numbers represented as ML. And then we have spin quantum numbers represented as S. So each of these have their own definition. So principal quantum numbers, which is N, is a type of quantum number that trying to indicate the energy level of the electron. So we are talking about 25th electron. So 25th electron is at which energy level? It's at 3. So the N is equal to 3 for the 5th electron, because the energy level where this 25th electron is located is 3. So the number that attached before these orbitals, they are called energy level. So we have 3 here. So this 3 is the energy level of the 25th electron. And then of course each and every orbital has its own azimuthal quantum numbers or subsidiary quantum numbers, which is L. Like for example, when L is equal to 0, you have S orbital. When L is equal to 1, you have P orbital. So when L is equal to 2, you have D orbital. When L is equal to 3, you have F orbital. So therefore, now the question is, the 25th electron is in which orbital? It is on D orbital. So it means that the value of L is going to be 2. So therefore now L is going to be 2. So we have L is 3. We have L is equal to 2. So then the next thing is magnetic quantum numbers, ladies and gentlemen. And you shouldn't forget that magnetic quantum numbers has a range of value from -0 to plus L. So therefore, if you have ML, which is the magnetic quantum numbers, has a value of minus L, 0 plus L. So the L here is 2. The L here is 2. It means that the magnetic quantum number of this 25th electron. So let's have the range of value of the magnetic quantum number when N is 2. So it's starting from -2, -1, 0, +1, and then +2. So you have 1, 2, 3, 4, 5. So we have 5 different options. So it means that the first box here is your -2. The second one is your -1. The third one is 0. Then this one +1. And this one is +2. So now, the 25th electron is on which orbital? Also is on which magnetic quantum number is at +2. So therefore, ML is equal to +2. I hope, ladies and gentlemen, this is very clear. Is that clear? Okay, excellent. And then the next thing is the magnetic quantum number. I didn't say anything about it. The magnetic quantum number is a type of quantum number that tries to give the orientation of the electron. And then the azimuthal quantum numbers, which is L, it gives the shape of the electron. While the spin S, the spin quantum number, it gives the direction of the electrons. So electrons generally arrange either clockwise direction or anti-clockwise direction. So when the arrowhead is pointing up, it is clockwise. When it is pointing down, it is anti-clockwise. And of course, the value for the clockwise is plus half, when electrons is pointing up, and when the electrons is pointing down, it is minus half. So now electrons, the 25th electron is pointing up, so it means that our spin quantum number is plus half. So that we have S is equal to plus half. So ladies and gentlemen, thank you very much. I think from here you can see clearly how you can use these quantum numbers to actually, or you can see from here, you can determine the position of the electrons using 4 quantum numbers. And also reverse is the case, you may be given quantum numbers and will be asked to determine the position of the electrons. So it is also very, very important. So let's actually delve more into this transition element. So now the next thing that we are going to look at is the properties of transition metal. The properties of transition element. So let me clean the board. So ladies and gentlemen, the next thing that we are going to look at is the properties of transition element. Properties of transition metals. What are these properties of transition metals? Number one, they have magnetic properties. They have magnetic properties. And these magnetic properties of transition element is divided into 3. A, transition metals can undergo paramagnetism. What is paramagnetism? Paramagnetism is the property of the transition element due to the presence of unpaired electrons. Unpaired electrons, like for example, unpaired electrons, let's say we have titanium with atomic number 22. So now we draw the electronic configuration as argon, we have 3d, and then we have 4s. So we have 4s2 and then 3d2. So for this 3d2, this is the one that we are going to look at. So number one, it has of course 5 soft shell. So you see the titanium have 1 electron here, then another 1 electron. So this is called unpaired electrons. They are called unpaired electrons because they did not pair with the electrons. So that is what they are called unpaired electrons. The electrons are arranged singly. And it's also applied like in the case of Newton's of maximum multiplicity, where he stated that electrons are arranged based on, so they are arranged in degenerate orbitals singly before pairing start taking place. So they are called unpaired electrons. So the magnetic properties of the element is due to their unpaired characteristics. So because they have unpaired electrons, that is why they can undergo paramagnetism. And in a simple way, we know that we have metal that they can easily be attracted by the metal. So what makes metal to attract metal or to attract material is due to the presence of unpaired electrons. So it means that a transition element can be attracted by the magnet due to their paramagnetism or due to their paramagnetism nature. And what makes them to have that paramagnetism nature is due to the presence of these unpaired electrons. We call it unpaired electrons. So then, apart from the paramagnetism properties, under these magnetic properties, we also have number 2, dimagnetism. Dimagnetism is the properties of a metal that actually they cannot attract with the metal. They cannot attract with any metal. Sorry, they cannot attract with any magnet. They cannot attract with any magnet due to the presence of paired electrons because they have paired electrons. So the electrons there are paired. Like for example, you know that why electrical wire, if you have a magnet that they cannot attract, is because they are made up of copper 1 plus, or they are made up of copper. And if you check copper from the electronic configuration, has atomic number 29. So we have argon configuration, and then we have 3d10, and then we have 4s. So you see, in this case, do we have any unpaired electrons? There is no unpaired electron because if you check the 3D, you'll see that all the electrons are completely filled with the electrons. So you see 1, 1, 1, 1, 1. So it will now be paired. Paired again, paired again, paired again, paired again. So there is no any unpaired electrons. So because they have paired electrons, that is why they are diamagnetism and they cannot be attracted by the magnet. So the next properties under these magnetic properties of the element is ferromagnetism, which is number C. This one is B. So we have number C, which is ferromagnetism. So in the case of ferromagnetism, is actually applied to the elements that are extremely paramagnetic. Like for example, which of the element is extremely paramagnetic, that can undergo or that has paramagnetic properties. Of course, in this case we can take manganese, atomic number 25. We have argon 4, we have 3d5, and then we have 4s2. So if you take this, you will realize that of course we have 1, 2, 3, 4, 5. Because of the number of paired electrons are many, so that is why they can extremely attracted toward magnet, and that is why they are called ferromagnetism. So the more the number of paired electrons, the more the magnetic properties of the metal. So that is actually one of the first properties of transition element. And then the next properties of transition element is variable oxidation state. Transition elements generally have variable oxidation state. So this is the second chemical of the second properties of transition element. So generally, transition element they have variable oxidation state. Unlike sodium, sodium has only one oxidation state, which is +1. Because when it loses one electron, it's not going to lose or get any electron. So it's not going to lose any other electron. So that is why they have constant variable oxidation states. But in the case of transition element, they have variable oxidation state. So their oxidation number can change. You can see it +1 here, you can see it +2 here, and you can see it +3. And why is it that this element they can undergo variable oxidation state is because they have small atomic size, and also they have close energy level. So that is why electrons can be reduced from 3d5 and can be reduced from 4s. It can be reduced from 3d and it can be reduced from 4s. So, ladies and gentlemen, why transition element have variable oxidation state? It's because of two reasons. Number one, the first reason why it has variable oxidation state is because the energy differences between the 3D and 4S is very small. It's very small. And that is why electron can be used from 3D and can also be used from 4s. Another reason why transition elements have variable oxidation states is because they have partially filled d-orbital. They have partially filled d-orbital. That is why they can undergo they can actually form variable oxidation state. So it's simple, ladies and gentlemen. In this case, when we are talking about variable oxidation state, manganese, like for example, in this case, you see the electron configuration of manganese 3d54s2. So manganese can lose one electron from here. So when you lose one electron from here, it means you are left with one. So it can be manganese 1 plus. So when 2 electrons is completely lost from the 4s, it's going to be manganese 2 plus. When 2 electrons from here and 1 electron is lost from here, it means that 3 electrons are lost. It means that we have manganese 3 plus. And when 2 electrons are lost from here, 2 electrons from here, we have manganese 4 plus. When 2 electrons are lost from here and 3 electrons are lost from here, it means that you have manganese 5 plus. 2 electrons from here and 5 here is going to be manganese 7 plus. So that is why transition elements will have variable oxidation states due to small energy differences between 4s and 3d, and also partially pure d-orbital. So that is why transition element form variable oxidation states. Then the next thing after the variability or variable oxidation states, the next properties is the ability to form a colored compounds. They have the ability to form color compound. That is one of the other properties of transition elements. So they have the ability to form color, and that is why, ladies and gentlemen, in most cases when you go to the lab and you see compound in color, that is to tell you that one of the components of that compound is a transition element, because they have the ability to form colored compound. And why transition have the ability to form colored compound is, of course, due to the presence of unpaired electrons. So the fourth property, the third one is formation of color compounds. The transition element, they have ability to form color compounds due to, the reason is because of the presence of unpaired electrons. And what is the link between these unpaired electrons and their color formation? Is because what usually happens is that these unpaired electrons in the transition element absorb photons. They absorb photons from visible light. They absorb photons from visible light and move from higher levels, and that makes them form color. So this is the reason why transition elements form color. You have unpaired electrons, and the presence of that unpaired electrons make them to absorb photons, and then from visible light, which make them to transit to higher level and make the compound form color. So this is actually the major reason why transition element form color. And then let me just give example. Like for example, if you can check copper 1 plus is colorless. It's colorless. Why is it that it is colorless? If you can check copper 1 plus, you can see that the 3D of copper is completely filled with electron. In addition, what if you take copper 2 plus? It is blue in color. It is blue in color. Why is it that it is blue in color? Because when you say copper 2 plus, it means that one electron is lost from 4s and 1 electron from 3D. So it means that there is 1 unpaired electrons, and that's what makes it to appear as blue in color. We have some of these metals like iron, brown in color, and all that including the presence of unpaired electrons. So ladies and gentlemen, this is actually one of another properties of transition element where they form color. Then the next properties of transition element is their ability to form complex ion, their ability to form complex compounds, their ability to form complex compound. So why did that transition element form complex compounds? Also at the same time is because this transition element, they have partially filled d-orbital, and of course they have the ability to accept lone pair of electrons. So this formation of complex is to repair two components. It's to repair two components. It needs ligands plus complex ion. So the complex ion is usually, or the central metal, let me just say not complex ion, the central metal ion, the central metal ion. So these central metal ions are usually transition elements because of the presence of unpaired electrons and partially filled orbitals. That is why they can form a complex compound with ligand and the central metal ion. So what is a ligand and what is a central metal ion? Although I'm going to make two videos, so for this one it's specifically on transition metal, so I will also do another video for ligands. So now, let me start with what is ligand. So a ligand, ladies and gentlemen, is simple. They are group of atoms or ions that donate lone pair of electrons. They are defined as an group of atoms that donate lone pair of electrons. Ligands, they are atoms or groups of atoms. They can be ions, or atoms. So they are ions, atoms, or group of atoms that donate lone pair of electrons. That is what we call ligands. So they are atoms or group of atoms that donate lone pair of electrons. That is what they are called ligands. And another way you can call them Lewis V's. Lewis V's. Why they are Lewis V's? Because they donate lone pair of electrons. And how do we know that a compound atoms or group of atoms is a ligand? For example, let's say we have ammonia and H3. So nitrogen in the ammonia has one lone pair of electrons. Of course, let's see the atomic number of nitrogen. So we have one electrons here, one, then we have 1, 2, 3, 4, then we have 5. So this is lone pair of electrons. So it means that in ammonia, we have nitrogen with one lone pair of electrons. So it means that it can donate this lone pair of electrons. So ammonia is a ligand, and how many lone pair of electrons is going to donate? 1, and that is why it is called monodentate ligands. So it is going to donate 1 lone pair of electrons. And then cyanides, also if you take cyanide, Cn, the nitrogen is here, it has lone pair of electrons. It is also another example of monodentate ligand. We have water, H2O. The oxygen has 2 lone pair of electrons, but it donates only 1 lone pair of electrons. It cannot donate all the 2, so it is also another example of monodentate ligand. So ladies and gentlemen, this is the ligand, and these are the different types of ligands that we have, and they donate different lone pair of electrons. And then the next thing, because I don't want to go deep into ligand here, so I'm going to make another video for ligands. So now, the next thing is the central metal ion. So a central metal ion are ions that usually accept lone pair of electrons. So they are the one that accept lone pair of electrons from the ligand. So that is why in the case of complex ion, you can see copper like this, bonded with different ligand like cyanide here, you have cyanides, you have another cyanide here, then you have another cyanide, then you can also have another cyanide. So you see 1, 2, 3, 4, 5, 6. So this is a typical example of complex ion. So it can be from hexacyanates, so Cn6. So this is examples of complex ion that is formed between ligand and the central metal ion. So the central metal ion, they are called Lewis acid because they are the one that accept their electrons, while the ligand, they are always be because they do not love their electrons. So ladies and gentlemen, this is basically on the general properties of transition element. So I think this is really clear. You now understand the concept of transition element, how to write their electronic configuration, and also their quantum numbers, as well as the properties of the transition element. So ladies and gentlemen, we are now going to meet in the next video on. Thank you.